Arjun, think about a single protein in your body. It's a tiny, intricate machine made of thousands of atoms, folding and vibrating millions of times a second to keep you alive. What if we could watch it work in slow motion at the atomic level?
For decades, that's been a holy grail of computational biology, and it seems a major collaboration has just taken a very significant step toward it.
Right. This is the news from IBM, the Cleveland Clinic, and the RIKEN Research Institute in Japan. The headline number is just staggering. They modeled a 12,635 atom protein complex, the largest ever simulated using a quantum computer.
It is, but the key is in that specific phrasing. Using a quantum computer. It wasn't simulated on a quantum computer, at least not entirely. The real breakthrough here is a methodology they're calling quantum-centric supercomputing.
Okay, that's an important distinction. What does that mean in practice? It's not just one giant quantum chip crunching the whole thing.
Exactly. Think of it as a hybrid approach. The vast majority of the work, calculating the forces and positions of most of those 12,000 plus atoms, was done on a classical supercomputer, the kind of work they do at a place like RIKEN, which has some of the most powerful machines on the planet.
So the supercomputer is the workhorse, handling the big picture.
Precisely. But there's always a small, critical part of the protein where classical physics and standard computational chemistry methods break down. This is usually the active site where the real chemical action happens. And for that specific, incredibly complex piece of the puzzle, they turned to an IBM quantum computer.
So it's like a factory assembly line building a car, but when it comes to tuning the engine with microscopic precision, they call in a specialist master craftsman who has a unique set of tools.
That's a perfect analogy. The unique tools in this case are for calculating the quantum mechanical behavior of electrons in that active site. On a classical computer, simulating these electron interactions accurately is what we call an exponentially scaling problem. Each additional electron you try to model makes the problem exponentially harder, and you quickly run out of computing power, even on a supercomputer.
Why is that part so much harder than the rest?
It comes down to something called strong correlation. For most of the protein, you can approximate the electrons as moving somewhat independently. But in the active site, especially if there's a metal ion involved, the electrons are so densely packed and interactive that their behaviors are deeply, inextricably linked. Their fates are intertwined.
Strongly correlated electrons. Okay.
Yeah, and our best classical methods like density functional theory, or DFT, they start to fail here. They produce errors. A quantum computer, however, is built on the principles of quantum mechanics. It speaks the same language as those electrons, so it's naturally suited to solving that specific, deeply quantum part of the problem with high accuracy.
Let's go back to the scale. 12,635 atoms. How big of a leap is that really?
It's a huge leap. Previous quantum chemistry simulations that were even remotely accurate were on the scale of a few dozen atoms, maybe 100. This is 2 orders of magnitude larger. We're moving from simulating small, isolated molecules in a vacuum to simulating a component of a real biological machine in a more realistic environment.
And this is different from something like AlphaFold, right? That also made waves in the protein world.
Completely different problems. AlphaFold is revolutionary for predicting the static 3D structure of a protein from its amino acid sequence. It tells you what the machine looks like after it's been built. This new research is about simulating the dynamics of the protein, how it moves, vibrates, and changes shape to perform its function. It's about understanding how the machine actually works moment by moment.
Which is crucial for things like designing a drug. You need to know how the machine is moving to figure out how to best jam its gears, so to speak.
Or to fix it, or to activate it. Yes, understanding dynamics is the next frontier, and it's a much harder computational problem than predicting a static structure.
The other big number I saw was a 210x accuracy boost. That sounds a bit like marketing. How do you even measure that?
It sounds like it, but it's actually the technical core of the achievement. It's not a comparison against classical computers. It's a comparison of the quantum computer's own results, with and without error correction.
So it's about making the quantum calculation itself usable.
Exactly. The quantum hardware we have today, even IBM's best, is noisy. Quantum bits, or qubits, are incredibly fragile. They get jostled by vibrations, temperature changes, stray magnetic fields. This creates errors in the calculation. The raw answer you get from the hardware is often mostly noise.
So the raw answer is garbage?
Not quite garbage, but very, very messy. The breakthrough is in the software techniques for mitigating that noise. The researchers used a method, likely a variant of zero-noise extrapolation, or ZNE, where they intentionally add more noise to the calculation in controlled steps. By seeing how the results change as noise increases, they can extrapolate backwards to what the result would be in a hypothetical zero-noise environment.
That's so counterintuitive. You fix a noisy system by making it even noisier.
It is, but it works. And in this case, it worked so well that the final error-mitigated answer was 210 times more accurate, meaning closer to the true theoretical value than the raw, noisy answer from the hardware. This shows that even with today's imperfect quantum computers, we can extract scientifically valid results if our software is smart enough.
So let's bring it all together. What is the actual workflow? What does this look like day to day for the researchers?
Okay, so you start with your 12,635 atom protein. The team at RIKEN likely ran a classical molecular dynamics simulation on their Fugaku supercomputer to model the overall movement. At some point, the Cleveland Clinic researchers, the domain experts, say, this part here, this active site, is where the interesting biology is happening, and our classical model is inaccurate.
So they flag the problem area.
Right. Then the IBM team takes a snapshot of that specific region. They formulate a quantum chemistry problem for just that handful of atoms and send it to an IBM quantum device, probably something like their 127-qubit Eagle processor. The quantum computer calculates the ground state energy of that small piece, and the sophisticated error mitigation software cleans up the result to get a highly accurate number.
And then what? They have that one number.
They feed that accurate energy value back into the classical simulation running on the supercomputer. This corrects the classical model, like a course correction for a spaceship. The supercomputer then continues the simulation for another tiny step in time, and the whole process repeats. It's a continuous feedback loop between the classical and quantum processors.
Wow. So when you say it's a collaboration, it's not just the people, it's the machines themselves collaborating. So the big question, how does this change things? Are we on the verge of quantum-designed drugs for cancer or Alzheimer's?
Not tomorrow, no. We have to be really clear about that. This paper is a proof of concept, a methods paper, as they say in academia. It's a demonstration that the technique is viable. It's a blueprint.
A blueprint for a new kind of science, it sounds like.
It really is. The importance isn't that they solved a major biological mystery in this paper. The importance is that they've built and validated a tool that might one day allow us to do that. They've shown that this hybrid quantum classical approach can work on problems of a scale that is truly relevant to biology and medicine. Before this, we weren't sure.
It feels like one of those moments where it's not the destination, but the first step on the path that's the real story. And the path itself is this entirely new way of combining our best computing tools.
That's exactly right. For the next decade, at least, this is what quantum advantage will look like. It won't be a quantum computer replacing your laptop or a supercomputer. It will be a specialized quantum processing unit working in harmony with classical machines, tackling the tiny, intractable problems that unlock the bigger picture.
So the big takeaway isn't just that they simulated a giant molecule, it's that they've built a solid bridge between our best classical supercomputers and our emerging quantum computers.
Exactly. They've shown the bridge can hold traffic. They've created a new kind of scientific instrument, and now the work of exploration and discovery with that instrument can begin.
A new tool in the matrix. Thanks, Arjun.
Anytime, Maya.